Long before the modern microscope became a familiar sight in laboratories and classrooms, humans were already captivated by the idea of seeing beyond what the naked eye could perceive. The roots of magnification reached deep into ancient history, to a time when curiosity itself was perhaps the greatest scientific tool. Around 710 before Christ, in the ancient city of Nimrud in Assyria, a small, carefully ground piece of crystal now known as the Nimrud lens may have served as a primitive magnifying glass or burning glass. While we cannot be certain exactly how it was used, its very existence suggests that the ancients were experimenting with ways to bend light and unlock the secrets of the minuscule. Centuries later, the desire to enhance human vision found new expression among the Romans. In the 1st century Anno Domini, Roman craftsmen began experimenting with glass, discovering that varying the thickness of glass pieces could create magnification. This early understanding of optics planted the seeds for the development of more sophisticated lenses. Yet, it would be many more centuries before lenses were shaped and polished with enough skill and precision to become practical tools for everyday use. By around 1000 Anno Domini, the reading stone emerged, a simple convex glass disc placed directly on top of text to enlarge its letters. This invention marked the first known vision aid, making the written word more accessible to those with failing eyesight. The reading stone was, in many ways, the ancestor of all magnifiers and microscopes that followed. A significant leap occurred in medieval Italy between the 13th and 14th centuries as artisans developed the first eyeglasses. Salvino d'Armate is often credited with crafting the first wearable eyeglasses in 1284. With eyeglasses, the use of glass to correct and enhance vision became personal and portable, and the science of lens making gradually advanced. Spectacle makers learned to grind and polish glass with increasing accuracy, producing clearer and more effective lenses. Amidst this backdrop of optical innovation, the stage was set for a revolutionary breakthrough, the invention of the microscope. Historians generally agree that the first compound microscope, a device using at least 2 lenses to achieve greater magnification than a single lens, emerged in the Netherlands around 1590. Dutch spectacle makers Hans and Zacharias Janssen are widely credited with this invention, though its true origin remains debated. The device they created consisted of multiple lenses arranged in a tube, capable of magnifying objects up to 10 times their actual size. While modest by modern standards, it opened an entirely new realm of observation. The early years of the compound microscope were marked by both fascination and skepticism. Images were often blurry, distorted by lens imperfections, and its practical uses were not yet widely understood. Nevertheless, the idea of seeing the invisible had taken hold. In 1609, the renowned Italian scientist Galileo Galilei turned his attention to magnification. Galileo built a compound microscope using a combination of convex and concave lenses. His design represented a significant step forward, and in 1624 he presented his improved instrument to the Accademia dei Lincei, an early scientific society. Galileo's work inspired further refinements and brought the concept of the microscope to the attention of Europe's scientific elite. Around this time, in 1625, the word microscope itself was coined. Giovanni Faber, a member of the Accademia dei Lincei, devised the term to describe Galileo's compound microscope, drawing from the Greek micro, meaning small, and scopin, to look at. The name captured the essence of the tool, a device for looking at the very small. As the 17th century progressed, the microscope began to emerge from the shadows of curiosity and novelty, stepping onto the stage of scientific discovery. In England, Robert Hooke's Micrographia, published in 1665, proved pivotal. Hooke's meticulously detailed illustrations and descriptions of objects viewed under the microscope, such as the intricate structure of a flea or the porous surface of cork, captured the public's imagination. In his observations of cork, Hooke introduced the term cell to describe the tiny, box-like structures he saw, though he could not have known their true significance. Micrographia brought the marvels of the microscopic world into popular consciousness, transforming the microscope from an instrument of wonder into a powerful tool for scientific investigation. Yet perhaps the most dramatic advances in microscopy during this period came not from those using compound microscopes, but from a Dutch draper named Antony van Leeuwenhoek. Working in the 1670s, Leeuwenhoek designed and built simple single-lens microscopes of astonishing quality. Though lacking the complexity of compound designs, his tiny hand-polished lenses could achieve magnifications up to 270 times. With these instruments, Leeuwenhoek became the first person to observe living cells and microorganisms, including what we now know as bacteria. His discoveries revealed a hidden world teeming with life, invisible to all who had come before him. As the centuries passed, the microscope continued to evolve. The 18th century saw the instrument grow in popularity, not just among scholars and scientists, but also among Europe's wealthy elite. Owning a microscope became a symbol of refinement and intellectual curiosity, as much an object of status as a tool for inquiry. Yet, for all their beauty and craftsmanship, these early instruments were still hampered by technical limitations. Images were frequently blurred or distorted by colored fringes, a result of the way lenses bent light of different wavelengths. A major breakthrough arrived in 1830 when Joseph Jackson Lister developed the achromatic lens. By carefully combining lenses made from different types of glass, Lister was able to reduce the blurring and color distortion that had plagued microscopes for centuries. This improvement brought a new level of clarity to microscopic observation, enabling scientists to see the fine details of cells and tissues with unprecedented sharpness. Throughout its long and storied history, the microscope has reflected the ongoing interplay between science, technology, and culture. Each advance in lens making and every new discovery beneath the lens has set the stage for further exploration, transforming medicine, biology, and countless other fields. By making the invisible visible, the microscope has not only deepened our understanding of the natural world, but also reshaped the very boundaries of human knowledge. Today, when we peer into a microscope, we participate in a tradition that stretches back thousands of years. A tradition born from curiosity, nurtured by craftsmanship, and propelled by the relentless desire to see more, to know more, to understand the world in ever finer detail. The journey from ancient Assyrian crystals to the sophisticated instruments of the modern laboratory is a testament to the ingenuity and persistence of those who sought to magnify the unseen. As we continue to explore the microscopic universe, we stand on the shoulders of countless inventors, artisans, and scientists who, piece by piece, brought the world of the very small into focus. To peer into the microscopic world is to enter a realm governed by the principles of magnification and resolution, two intertwined concepts that form the foundation of every observation made through a microscope. Magnification enlarges the apparent size of an object, making the invisible visible, while resolution is the true test of a microscope, its ability to distinguish two closely positioned points as separate entities. Without sufficient resolution, magnification alone would produce only a larger blur, not the delicate structures and details that captivate scientists and students alike. The interplay between these two factors has shaped the evolution of microscopes, driving inventors and researchers to refine their instruments over the centuries. At its core, magnification begins with the lens. A magnifying glass, or simple microscope, uses a single biconvex lens curved on both sides to bend light rays so they converge, producing a larger image of the object. This straightforward design offers a modest increase in size, perfect for examining grains of sand, the texture of paper, or the intricate veins of a leaf. Yet, the desire to see further, to uncover the fine details of fabrics or the cells in a drop of pond water, demanded more. Here, the compound microscope comes into play, combining the powers of two lens systems, an objective lens, positioned close to the specimen, and an eyepiece, through which the observer looks. The total magnification is the product of these two lenses, so if both the objective and eyepiece magnify tenfold, the image appears 100 times larger than its actual size. This leap enables the exploration of an extraordinary range of biological and material wonders. But the quest for clarity goes beyond size alone. Resolution is the microscope's promise to separate what is truly distinct from what only appears so, a challenge dictated by the physical properties of light and glass. The sharpness of detail, or resolving power, depends on two critical factors: the numerical aperture, or NA, of the lens system, and the wavelength of light used to illuminate the specimen. Numerical aperture measures how effectively a lens can gather light and resolve fine specimen detail at a fixed distance. A higher NA allows the lens to capture more divergent rays from the sample, revealing finer features. Meanwhile, light itself imposes a fundamental constraint. Shorter wavelengths can distinguish smaller details, while longer wavelengths blur them together. This is why violet light, with its shorter wavelength, can theoretically resolve finer structures than red light. Even the best lenses in the shortest visible wavelengths face a fundamental boundary, the diffraction limit. At the heart of this limit is the wave nature of light, which causes it to spread when passing through small apertures or around edges. As formulated by Ernst Abbe and expressed through his famous equation, there is a minimum distance, about half the wavelength of the illuminating light, below which 2 points can no longer be distinguished. The Rayleigh criterion further refines this principle, setting a benchmark for when 2 points are just resolved. Beyond these limits, no amount of optical ingenuity can separate one point from another. The image blurs into ambiguity. This is why, for many years, optical microscopes could not reveal the intricate substructure of cells or the tiniest viruses. They were simply too small, too close together to be resolved by visible light. Within these constraints, an impressive family of optical microscopes has flourished. Each variant harnesses the interplay of lenses and light in unique ways to suit different investigative needs. The classic compound microscope is the workhorse of biology laboratories, providing clear, magnified images of thin slices of plant tissues or stained animal cells. The stereo, or dissecting microscope, uses two separate optical paths to create a three-dimensional view, invaluable for tasks like sorting insects or assembling tiny electronic components. Inverted microscopes reverse the position of lenses and light source, allowing observation of living cells in culture dishes from below, a boon for cell biology and medical research. Fluorescence microscopes open a window onto the world of glowing molecules. By bathing specimens in light of one wavelength and detecting the glow emitted at another, these instruments reveal structures and processes invisible to the naked eye, from the dance of chromosomes to the spread of pathogens. Phase contrast microscopes, meanwhile, exploit subtle shifts in the phase of light passing through transparent specimens, rendering the invisible contours of live, unstained cells visible in shades of gray. Confocal microscopes take precision further, using laser light and pinholes to scan and assemble crisp, optical slices of thick specimens, building up detailed three-dimensional reconstructions. Each of these optical tools is tailored for a specific scientific challenge, balancing the strengths of magnification, resolution, and imaging depth. Yet, the desire to see the truly minuscule viruses, individual proteins, even the arrangement of atoms, requires a leap beyond the diffraction limit of light. Here, electron microscopes take center stage, harnessing beams of electrons instead of photons. Because electrons have wavelengths thousands of times shorter than visible light, they can reveal details at the nanometer and even sub-nanometer scale. The mechanisms that drive electron microscopes are as ingenious as they are complex. Instead of glass lenses, these instruments use magnetic fields to focus the electron beams. In a transmission electron microscope, or TEM, electrons pass through an ultra-thin sample, producing images with astonishing internal detail, perfect for viewing the intricate architecture of cells, viruses, and even the spacing of atoms and crystals. Scanning electron microscopes, or SEMs, take a different approach. Electrons scan the surface of a specimen, and detectors gather signals produced by their interactions. The resulting images are crisp, three-dimensional renderings of surfaces, from the minute hairs on a fly's leg to the contours of a microchip. Not all advances rely on light or electrons. Scanning probe microscopes, such as the scanning tunneling microscope, STM, operate by bringing a needle-like probe so close to a surface that it can sense the arrangement of individual atoms. As the probe moves across the sample, it records tiny changes in electrical current or forces, building up an image with atomic precision. These instruments have expanded the realm of the visible to previously unimaginable scales, allowing scientists to study surfaces atom by atom. Alongside these advances, digital technology has transformed how microscopes are used and shared. Digital microscopes integrate cameras and digital sensors, capturing images and transmitting them to screens or computers in real time. This has opened new possibilities for analysis, collaboration, and education. Students can view the same specimen simultaneously, researchers can archive and share high-resolution images, and automated software can analyze thousands of samples at once. Each type of microscope brings its own strengths and limitations, making it uniquely suited to particular scientific, educational, or industrial tasks. Optical microscopes excel at imaging living tissues, colored specimens, and quick surveys, but are bound by the diffraction limit. Electron microscopes offer breathtaking resolution but require vacuum chambers, special sample preparation, and cannot image living organisms. Scanning probe microscopes achieve atomic detail but only for surfaces and often over small areas. Digital microscopes offer convenience and connectivity, yet depend on the underlying optics or sensors for their resolving power. The world of microscopy is not defined by a single instrument but by a toolkit, each piece designed to answer a different set of questions. As scientists continue to push the boundaries of what can be seen and measured, the interplay of magnification and resolution remains at the heart of discovery, ensuring that the microscope, in all its forms, continues to illuminate the hidden architectures of our world. Imagine a world where the boundaries of nature recede before your eyes, where a once blank, unyielding surface transforms into a vibrant metropolis of living forms and intricate patterns. This is the world the microscope has revealed to science and society alike. With a simple twist of focus, an entire universe comes into view. One that has shaped the very core of modern biology, medicine, and materials science, and continues to redefine the frontiers of human knowledge. When the earliest investigators peered through their lenses, they saw more than just strange shapes and patterns. They encountered living evidence of worlds previously undreamed of. The microscope's power to make the invisible visible laid the groundwork for entirely new scientific disciplines. In biology, the discovery of cells, bacteria, and countless microorganisms was not just a technical achievement, but a conceptual breakthrough. The existence of these tiny entities, once completely unknown, prompted a reimagining of what it means to be alive. Scientists realized that every plant, animal, and human is composed of microscopic units, each teeming with activity. These insights became the foundation of cell theory and launched the field of microbiology, forever changing our relationship with the natural world. The story of microscopy is filled with moments of wonder. When Robert Hooke and Antony van Leeuwenhoek first described their observations, their discovery sent ripples through the scientific community. Suddenly, blood was no longer just a red liquid, but a flowing river of cells, each with its own shape and function. In the froth of fermenting beer, yeast appeared as living organisms rather than inert powder. Stagnant pond water teemed with darting bacteria and other minuscule forms. These early glimpses shattered the illusion of emptiness and ignited a curiosity that would propel generations of scientists forward. As the microscope unveiled what had always been present but unseen, its influence quickly extended beyond the curiosity of naturalists. In medicine, its impact was transformative. For centuries, the causes of many diseases remained mysterious. Physicians could describe symptoms, but the agents of illness were invisible and, therefore, unknowable. The microscope changed that. With this new tool, doctors and researchers could finally observe pathogens directly, watching as bacteria invaded tissues or as abnormal cells multiplied in the blood. The microscope became indispensable in diagnosing diseases and paved the way for the acceptance of germ theory. The idea that many illnesses are caused by living organisms too small to see unaided. This understanding revolutionized infection control, surgery, and public health, saving countless lives. The microscope's value in medicine grew alongside technical innovations. When Joseph Jackson Lister introduced the achromatic lens in 1830, image clarity improved dramatically. No longer plagued by colored fringes and blurs, scientists could now distinguish fine details within cells and tissues. This leap in clarity made microscopes essential in both research and clinical laboratories. Doctors learned to recognize subtle differences between healthy and diseased tissue, to identify parasites in blood, and to classify bacteria by their shape and staining patterns. Each discovery not only improved patient care but also deepened our understanding of the body's hidden workings. Yet the microscope's power extended far beyond the living cell. In material science, forensic investigations, environmental studies, and pharmaceutical research, the ability to examine structures at the microscopic level opened new avenues of inquiry and innovation. Material scientists used microscopes to scrutinize the arrangement of cells and materials, revealing flaws invisible to the naked eye and leading to stronger, more reliable products. Forensic experts examined fibers, hair, and dust, piecing together evidence from the tiniest clues. Environmental scientists track pollutants and microorganisms in water and soil, while pharmaceutical researchers analyze the effects of drugs on cells and tissues, refining therapies with unprecedented precision. As the demands of science increased, so did the capabilities of microscopes. The advent of fluorescence microscopy allowed researchers to tag specific molecules within cells, causing them to glow under certain conditions. This technique transformed cell biology, enabling scientists to trace the movements of proteins, follow the progress of infections, and observe the intricate dance of cellular machinery in real time. Confocal microscopy built on this by creating optical slices through thick specimens and assembling three-dimensional reconstructions. Suddenly, researchers could explore the architecture of tissues and organs, examining their depths layer by layer. Phase contrast microscopy, meanwhile, made it possible to visualize live, unstained cells, capturing the subtle contours and dynamic changes that define life at its most fundamental level. These technical advances have become central to how we educate, diagnose, and treat. In medical schools, students now learn to recognize disease by examining tissue samples under the microscope, linking textbook descriptions with the living reality of cells. In research, the microscope serves as a bridge between theory and practice, allowing scientists to test hypotheses and observe results directly. Diagnostic laboratories rely on microscopy to detect infections, identify cancer cells, and monitor the effects of new treatments. This ability to see, to truly see, has made early detection of diseases possible, transformed drug development, and laid the groundwork for personalized medicine, where therapies are tailored to the unique cellular makeup of each patient. The impact of microscopy reaches far beyond the laboratory or hospital ward. With the global microscopy market expanding, driven by rapid technological advancements and a growing range of applications in life sciences, nanotechnology, and material science, the reach of these instruments is broader than ever. Where once a microscope was a rare and precious tool, found only in the hands of specialists, today digital and portable models are widely available. In classrooms around the world, children peer through lenses or watch digital displays, marveling at the hidden complexity of a leaf or the structure of a fly's wing. In clinics and field stations, portable microscopes bring diagnostic power to remote villages and disaster zones, narrowing the gap between cutting-edge science and everyday life. The social and cultural impact of the microscope is difficult to overstate. By making the invisible visible, this instrument has transformed not only science but also our collective imagination. It has forced us to reconsider the boundaries of the natural world and our place within it. Once, people could only speculate about the causes of disease, the workings of the body, or the structure of materials. Now, thanks to the microscope, we have evidence, not just in books or theories, but in the tangible, observable world beneath the lens. The microscope has become a symbol of inquiry, a testament to the power of observation and a tool for democratizing knowledge. At the same time, the story of the microscope is still unfolding. New techniques and technologies are emerging rapidly, continually expanding the horizons of what can be seen and understood. The quest for greater resolution, faster imaging, and more accessible instruments drives innovation in fields as diverse as cancer research, environmental monitoring, and forensic science. As microscopes become more user-friendly and affordable, their influence seeps further into our daily lives, shaping how we learn, how we diagnose, and how we imagine the world. Ultimately, the microscope's greatest legacy may be the sense of wonder it inspires. Every time a scientist, student, or curious observer gazes through a lens and witnesses a previously hidden world spring to life, the boundaries of knowledge are pushed outward. It is a reminder that there is always more to see, more to discover, and more to understand. In this sense, the microscope is not just an instrument of science, but a gateway to curiosity, a tool that continually unlocks the invisible, inviting us to explore the mysteries that lie just beyond the reach of our everyday vision. Imagine standing at the edge of a vast hidden landscape, one that has always existed yet remained invisible to human eyes until the ingenuity of lens makers and scientists made it accessible. Today, the microscope remains our vessel for this journey, but the landscape itself has changed in ways early pioneers could scarcely have imagined. As we look toward the future of microscopy, the boundaries of what can be seen and analyzed are expanding, not just through sharper lenses, but through remarkable new methods, computational power, and the transformative force of digital technology. In the past, microscopes were limited by the so-called diffraction limit, a physical constraint that seemed as immovable as a mountain. No amount of polishing or stacking lenses could enable optical microscopes to distinguish details smaller than about 200 nanometers. Yet in recent years, scientists have found ways to bypass this limit entirely. Enter the age of super-resolution microscopy, a family of techniques that has redrawn the map of the microscopic world. Using methods such as stimulated emission depletion, photoactivated localization microscopy, and stochastic optical reconstruction microscopy, researchers can now resolve structures as small as 10 nanometers or even finer, revealing details once accessible only to electron microscopes. These innovations work not by simply magnifying, but by manipulating the very physics of light-switching fluorescent molecules on and off, or using carefully orchestrated laser pulses to sharpen images beyond what traditional optics would allow. The result is a view into the intricate architecture of cells, proteins, and materials on a scale that was, until recently, unthinkable for light-based instruments. But super-resolution is only the beginning. Expansion microscopy offers a different approach. Instead of seeing smaller with better optics, it physically enlarges the specimen itself. By embedding biological samples in a special gel and then swelling the gel, researchers can spread out fine structures within tissues, making them accessible to conventional microscopes. This clever reversal, making the tiny big, rather than making the big tiny, has allowed scientists to explore the molecular organization of complex tissues with a clarity that was previously unattainable. Meanwhile, light sheet fluorescence microscopy has opened up new vistas for observing living tissues and large biological samples. By illuminating specimens with a thin sheet of light rather than a broad beam, this technique minimizes damage and enables high-speed, three-dimensional imaging of delicate processes as they unfold in real time. Imagine watching the development of an embryo or the migration of immune cells through a living organ, not as a series of static snapshots, but as a vivid, moving panorama. Such capabilities promise to deepen our understanding of life's most dynamic and intricate moments. As powerful as these optical advances are, the real revolution may be happening in the digital realm. The integration of artificial intelligence, machine learning, and automated image analysis is transforming how scientists and clinicians interact with microscopes. No longer limited to what the human eye can interpret, digital systems can now sift through vast quantities of imagery, flagging subtle patterns or anomalies that might elude even the most experienced observer. In research laboratories and pathology departments alike, artificial intelligence-supported diagnostics are becoming increasingly common, accelerating workflows and supporting more consistent, accurate interpretations. Digital slides can be shared instantly across continents, enabling remote consultations and collaborative discoveries that transcend the barriers of distance. The microscope is also shedding some of its traditional baggage. Emerging trends like lens-free computational imaging and on-chip microscopy are reimagining the very structure of the instrument itself. By forgoing bulky lenses, these systems use sophisticated algorithms and microfabricated sensors to reconstruct detailed images over wide fields of view. Such approaches hold promise for portable, high-throughput analysis. Imagine entire classrooms, clinics, or remote field stations equipped with tiny devices that can survey vast numbers of samples at once, all without the need for delicate optics. The economic and scientific appetite for these innovations is unmistakable. The global market for advanced microscopy, including super-resolution and digital systems, is projected to grow significantly in the coming years. This demand is driven not only by the needs of biomedical research, where the ability to see ever deeper into the cell can mean the difference between understanding and mystery, but also by diagnostics and material science. As the tools become more sophisticated, their influence spreads, touching everything from the design of new drugs to the analysis of advanced materials and the early detection of disease. Looking ahead, the convergence of microscopy with big data analytics, artificial intelligence, and machine learning is poised to accelerate discovery even further. Algorithms trained on thousands or millions of images can identify subtle features, track changes over time, and suggest new avenues of investigation. Automation is making it possible to screen enormous numbers of samples without human intervention, freeing scientists to focus on the creative and interpretive aspects of research. The microscope, once a solitary tool at the workbench, is becoming the hub of a digital ecosystem where insights emerge not only from what is seen, but from how information is analyzed and connected. The horizon is dotted with concepts that, though still in their infancy, hint at the next great leaps. Smart and adaptive imaging systems could one day adjust themselves in real time, optimizing focus, illumination, and even magnification on the fly based on the sample's properties. Multimodal and high-throughput microscopes could combine several imaging techniques within a single platform, switching seamlessly between fluorescence, phase contrast, and computational modes to provide a more complete picture of complex specimens. The promise of real-time, in vivo imaging peering into living organisms without removing or staining tissues suggests a future where disease can be diagnosed and monitored directly as it unfolds. Remote control microscopy may soon allow experts to operate instruments located thousands of miles away, bringing cutting-edge diagnostics to underserved regions. Through all these changes, one constant remains: the microscope's ability to turn the invisible into the visible, to make the unknown knowable. The sense of wonder that greeted the first glimpses of cells and microbes has not faded, it has only deepened as new layers of complexity are revealed. With each breakthrough, whether it is a sharper image, a faster scan, or a more sensitive detector, the boundaries of our knowledge are pushed outward, and as those boundaries expand, so too does our sense of possibility. The microscope's future is not simply about seeing smaller or faster. It is about reimagining the very nature of observation itself: who can look, what can be seen, and how we make sense of the patterns that emerge. With the continued integration of artificial intelligence, digital sharing, and adaptive optics, the microscope will likely become more accessible, more powerful, and more deeply woven into the fabric of discovery than ever before. Microscopy is expected to remain at the forefront of scientific innovation, enabling new insights into biology, medicine, and materials at scales that defy imagination. Whether unraveling the mysteries of the brain, diagnosing disease before symptoms appear, or designing the next generation of materials, the microscope stands as both tool and symbol, a testament to humanity's relentless curiosity and its drive to illuminate what was once hidden. As we look ahead, the invisible world is not receding but unfolding, one astonishing detail at a time.